All right, so we're going deep into biopharmaceutics today. You gave us like a ton of material on this, so it's pretty clear that this is important stuff,
Yeah.
especially when you look at all the different meds and all the different ways we take medicine.
Yeah, it's really fascinating. My background is in biopharmaceutics, and it's really opened my eyes to how many different factors affect, how drugs actually work in our bodies. It's not just like you swallow a pill and hope for the best.
Yeah, no kidding. To be honest with you, I'm a little overwhelmed by all this information. Where do we even begin? Like, what's the main thing we should be focusing on for this deep dive?
Well, think of this deep dive like a journey. Okay.
Yeah.
We're going to follow a drug, like from the very beginning when you take it all the way to where it's supposed to go in the body. We'll look at all the things that help it along the way and all the things that might slow it down or even stop it from getting where it's supposed to be.
Okay, that helps. So it's like a tiny little obstacle course that the medication has to get through.
Exactly.
So what exactly is biopharmaceutics? How does it play into all of this?
Well, biopharmaceutics is really the study of how a drug's physical and chemical properties, things like its size, its shape, how soluble it is, how all these things impact how it behaves in the body. It also looks at how the drug is formulated, those inactive ingredients that actually have a surprising effect on how well it works.
So it's not just about the drug itself. It's about all the other stuff that comes along with it, in a pill or a capsule or whatever.
Absolutely. It's like a recipe.
Yeah.
You need the right ingredients and the right amounts to make the dish work. And in this case, getting the recipe right can be the difference between a drug that works and a drug that doesn't.
Okay, that makes sense. So let's talk about the journey then.
Yeah.
What are the key steps along the way?
Huh.
Let's say for a pill that I swallow. What happens?
All right, so let's imagine you just took a tablet. First thing that needs to happen is it needs to disintegrate. It needs to break apart in your stomach.
Oh, so it's not like the pill just goes down whole. It has to actually break up first.
Exactly.
Yeah.
Then comes the dissolution part. So now all those little drug particles that have broken up, they have to dissolve into your stomach fluids, kind of like when you dissolve sugar in water.
Got it. So first the pill breaks up, and then all those little bits have to mix in with the liquid in my stomach.
Yep, you got it. Only then can that final and most important step happen: absorption. This is where the drug molecules actually cross the lining of your gut and enter the bloodstream. That's how they can be carried to their target.
Okay, so it's a three-step process: disintegrate, dissolve, absorb. Seems pretty straightforward.
Yeah.
But you mentioned something earlier called a rate-limiting step. What is that all about?
Yeah, that's really important. The slowest of those three steps actually dictates how quickly the whole process happens. So imagine a relay race, right? Even if your last runner is super fast, if the first runner is really slow, it's going to hold the whole team back.
That's a great way to picture it. So if a drug dissolves really slowly, it doesn't really matter how fast it can be absorbed. That slow dissolving is going to hold everything up.
Exactly. And that's why things like particle size are so important. Think about if you try to dissolve a sugar cube versus granulated sugar, those smaller particles are going to dissolve way faster.
So for some medications, if they just ground the drug up into a finer powder, it could make a big difference in how well it works.
Absolutely. It's one of the ways we can use biopharmaceutics to actually optimize drug delivery. Now, each drug has its own set of properties that's going to influence this journey.
Okay, so it's not just a one-size-fits-all approach. Every drug is a little different. So what are some of the key properties, the things that kind of make each drug unique?
Well, solubility is a big one. This is how easily a drug dissolves in water. And as we've seen, that is essential for absorption. Some drugs are like salt, they dissolve instantly. Others are more like oil and water, they just don't want to mix.
I can picture that.
Yeah.
So some drugs are naturally better at dissolving than others. What else do we need to think about?
Well, there's also stability. This is how well the drug holds up in different environments. Your stomach can be a pretty harsh place with all that acid. Some drugs are really delicate, and they can actually break down before they even have a chance to be absorbed.
It's like sending a package through, a rough shipping system. Some need extra protection to make it to their destination.
Exactly. And we've already talked about particle size, but there's another really interesting factor called polymorphism. You see, some drugs can actually exist in different crystal forms, kind of like how carbon can be found as both a diamond and as graphite.
Wait, so the same drug can actually have different versions of itself.
Yeah.
And these versions actually act differently.
Exactly. These different forms can have different solubilities. And this is going to affect how well the drug is absorbed. It's like the drug is wearing different outfits, each impacting how it interacts with its environment.
Wow, that's incredible. It's amazing how even tiny differences in the structure of a drug can make such a big impact.
For example, the antibiotic chloramphenicol. It actually has several different crystal forms, and the beta form is way more soluble. This leads to much higher drug levels in the body.
So it's all about understanding these little drug personalities and figuring out the best way to deliver them.
That's a great way to put it. But remember, it's not just about the drug itself. We also have to think about those inactive ingredients, those excipients that go into the formulation.
You mean the other stuff that's in the pill or capsule besides the actual drug? I always thought that was just filler stuff. Not really that important.
Oh, there's so much more than just filler. Excipients can impact everything from the manufacturing process to the stability of the drug. They can affect the taste and even the absorption rate. Some can enhance the solubility, while others can slow it down for a controlled release.
So they're kind of like the behind-the-scenes crew for a movie. The editors, the sound engineers, the lighting people, they don't appear on screen, but they're essential to making the final product work.
Exactly. Think about disintegrants like starch. They help those tablets break apart quickly in the stomach. Or lubricants like magnesium stearate, which can actually hinder dissolution if you use too much. It's all about finding the right balance.
So formulating a drug is like a science and an art. You need to understand all these different factors and how they all work together to create something that actually works.
Exactly.
Well, I think this is a great place to pause for now. We've already covered so much ground just in this first part of our deep dive. We've talked about, the basics of how drugs get absorbed by the body and the challenges of making sure that they dissolve properly.
Yeah.
We even touched upon the amazing world of nanotechnology, but there's still so much more to explore.
Yeah, there is.
So let's take a quick break and we'll come back and continue our journey through the world of biopharmaceutics. It really does sound like creating a drug is like, coming up with this really complex recipe. You need to know how every ingredient interacts with each other.
Yeah, that's a great analogy. It's all about finding the perfect balance to make sure that the drug's delivered the way it's supposed to be.
Okay, so we've got the drug itself, and we've got all these excipients. And they all have to work together to get through that three-step obstacle course: disintegrate, dissolve, and absorb. But how do scientists actually know if it's working? It's not like they can watch it happening inside someone's stomach.
Right. That's where dissolution testing comes in. It's basically like a miniature version of your digestive system, but in a lab setting, we use this special equipment to mimic the conditions in your stomach and your intestines, and we can actually measure how fast a drug dissolves from, like a tablet or a capsule.
So it's like they recreate that obstacle course, but in a test tube?
Exactly.
How do they make sure that a test tube is a good stand-in for a real stomach?
Well, we have to carefully control the conditions. Make sure the temperature is right, the amount of liquid, the type of fluid. We want to make sure it's as close as possible to what's actually happening in your body. There's even something called a sink condition.
A sink condition. What is that?
It basically just means making sure there's always enough fresh liquid for the drug to dissolve into. So think about if you're dissolving sugar in a small glass of water. Eventually, that water is going to get saturated and no more sugar can dissolve, right? In dissolution testing, we want to prevent that. So we use a large volume of liquid so we can accurately measure how fast the drug dissolves without it getting stuck.
Okay, that makes sense.
Okay.
So dissolution testing helps scientists see how a drug is going to behave in the body.
Yeah.
And then they can use that information to optimize the formulation.
Right. It's all about making sure that the quality is consistent and that the drug is going to perform the way it's supposed to. And it's actually fascinating to see how even tiny little changes in the formulation can have a big impact on that dissolution rate and therefore the effectiveness of the drug.
It really shows you how powerful biopharmaceutics is. So far, we've been talking mostly about, pills and capsules. But you mentioned earlier that these principles apply to all kinds of different drug delivery methods. Can you give me some examples?
Absolutely. Let's take fenofibrate. It's a medication that's used to lower cholesterol. You might know it by the brand name Tricor. This drug is actually a great example of how understanding biopharmaceutics can lead to big improvements in drug delivery over time.
Okay, I'm interested. Tell me about the evolution of fenofibrate. What were the challenges and how did biopharmaceutics help solve them?
Well, fenofibrate is what we call a poorly soluble drug. So imagine trying to dissolve sand in water. It's just not going to happen very easily. This poor solubility meant that the original capsule form of fenofibrate had very low and inconsistent bioavailability.
So even if someone was taking the medication exactly as prescribed, their body might not have been absorbing enough of the drug for it to actually work.
Exactly. So scientists had to find a way to improve its solubility. They discovered that by micronizing the drug, basically grinding it into much smaller particles, like turning coarse sand into fine dust, they could actually significantly improve its dissolution and therefore improve its bioavailability. This led to the creation of Tricor, which is a micronized capsule formulation.
So they made the drug particles smaller so they could dissolve more easily in the stomach.
Mm.
It's kind of like when you grind up your coffee beans, you get a better cup of coffee.
Exactly. But even with micronization, there were still challenges. Researchers found that taking Tricor with food, especially a high-fat meal, could actually increase the amount of drug absorbed by as much as 35%.
Hold on. So what you eat can actually change how well a medication works.
It really highlights how complex the relationship is between our diet and the medications we take. In the case of Tricor, a fatty meal was actually enhancing the absorption, which could lead to really unpredictable drug levels in the body.
So it's not just about taking the right dose, it's also about understanding how other factors like food can affect how the drug is absorbed.
That's really good to know. Did scientists find a way to kind of overcome this food effect with Tricor?
They did. And this is where things get really cool. They turned to nanotechnology. By creating a nano-sized version of fenofibrate, they were actually able to overcome that food effect and create a tablet version of Tricor that could be taken without regard to meals. Nanotechnology, now we're talking. It sounds futuristic. So they basically shrunk those drug particles down even further, making them so tiny that food couldn't interfere with their absorption.
Exactly. They essentially created this tiny microscopic delivery system that protected the drug and allowed it to be absorbed consistently no matter what was going on in the stomach.
It's like they gave the drug a little suit of armor to help it get through the digestive system. So, problem solved, right?
Well, not quite. You see, the story of fenofibrate doesn't end there. Remember how we talked about drugs having different personalities? Well, fenofibric acid, the active form of fenofibrate, is also poorly soluble.
So even though they found a way to deliver fenofibrate effectively, they were still dealing with solubility issues with its active form. What did they do about that?
This is where things get really clever. They decided to explore a different approach, creating a salt form of the drug.
A salt form, like table salt? What does that have to do with drug delivery?
It's all about the chemistry. By creating a salt form of fenofibric acid, specifically the choline salt, they were actually able to dramatically change its solubility. This new form dissolves way more easily in water, leading to faster and more consistent absorption.
So they basically gave the drug a makeover, transforming it into a more soluble, easier to absorb version of itself.
Exactly, and it led to the development of Trilipix, which is a delayed-release capsule form of fenofibric acid that is also food-independent. So it's a really fantastic example of how a deep understanding of biopharmaceutics can lead to a whole range of different solutions for these tricky drug delivery problems.
It's incredible to see how one drug can go through so many different transformations, all because, scientists are trying to optimize its delivery and make sure that patients are getting the most benefit from their medication. It's like a constant evolution, always striving for better solutions.
Exactly, and it's not just about oral medications either. Remember, these same principles apply to all different kinds of drug delivery methods, from injections to inhalers to patches.
Wow. So we've covered a lot of ground here. We've talked about the basics of drug absorption, the challenges of solubility, the role of all those excipients, and even the amazing world of nanotechnology. What else is out there on the horizon of biopharmaceutics? What are the next big things? It's really amazing to think about how far we've come from just, grinding up a drug to make it dissolve better to actually like engineering nanoparticles to deliver medication. It feels like the possibilities are endless. What are some of the areas that you're most excited about in the future of drug delivery?
One area that's really exploding right now is targeted drug delivery.
Targeted drug delivery. What does that mean?
So instead of just like flooding the whole body with a drug, what if we could deliver it only to the specific cells or tissues where it's needed? It's like sending a package right to its destination instead of just dropping it off somewhere in the neighborhood and hoping it finds the right house.
Okay, yeah, I can see how that would be a game changer. It's especially for something like chemotherapy, where you're trying to kill the cancer cells without harming the healthy tissue. But how do you actually target a drug to a specific place in the body? It's not like there are little zip codes for individual cells.
It's definitely a complex process, but researchers are developing some really, really ingenious strategies. One approach is to attach antibodies to the drug, and these antibodies act kind of like homing devices. They go and seek out and bind to specific markers on those target cells. It's like putting a special address label on the package that only that cell can read.
So it's all about finding the right address for the drug to be delivered to. That's pretty cool.
Yeah.
What are some of the ways to target drugs?
Another way is to encapsulate the drug in these nanoparticles. These
Hmm.
are like tiny little carriers that can be engineered to have specific properties that allow them to accumulate in certain tissues or organs. For example, some nanoparticles are naturally drawn to areas of inflammation, so that makes them ideal for delivering drugs to treat things like arthritis.
So instead of just floating around in the bloodstream, these nanoparticles actually have their own little GPS system that directs them to the right spot.
You could think of it that way. And it gets even more interesting. Researchers are looking at using genetically modified viruses to deliver drugs.
Wait, viruses? I thought viruses were bad. Aren't those dangerous?
Don't worry, these viruses are carefully engineered to be safe. They're not going to cause any harm. They're basically just carrying their therapeutic cargo. They've been reprogrammed to deliver the drug instead of causing disease.
So we can use these tiny little biological machines to create these incredibly precise drug delivery systems. It's like we're entering a whole new world of medicine.
We are. And this precision is only going to get better as we understand more and more about biopharmaceutics. We're already seeing really impressive progress in areas like personalized medicine, where treatments are tailored to a person's unique genetic makeup and how their body processes drugs.
Personalized medicine. So in the future, we could actually have medications that are custom designed for each person.
Exactly. It's moving away from this one-size-fits-all approach to healthcare. By understanding how differences in our genes, our bodies, affect how we respond to drugs, we can start developing treatments that are more effective and have fewer side effects.
That sounds like the ultimate goal of medicine, finding the right treatment for the right person at the right time. And it sounds like biopharmaceutics is playing a huge role in making that happen.
It really is. It's kind of the invisible force that shapes how medications work in our bodies. By understanding all those intricate connections between a drug's properties, its formulation, and our own biological processes, we can really unlock the full potential of medicine.
That's a great way to wrap up our deep dive today.
Yeah.
We've talked about so much, from the very basics of how drugs get absorbed to the mind-blowing possibilities of targeted drug delivery and personalized medicine.
It's been a really fascinating conversation, and I hope our listeners are as excited about the future of biopharmaceutics as we are.
I definitely am. And here's something for you to think about as you continue to explore this world. Think about the medications you take. What are their delivery methods? Can you find any information about their biopharmaceutic properties? And how might those properties affect your own experience with those medications? Keep learning, keep asking questions. And as always, thanks for joining us on the Deep Dive.